Welcome back to the Quiet Explainer. Today, we are exploring the architecture of the Internet, how data travels. This is a long journey, nearly 2 hours. You do not need to understand everything at once. You can simply listen. Let the structure form slowly. There is no pressure to keep up, no rush to take notes. If you find value in calm, structured explanations like this, you can subscribe and return anytime. Now, let's begin at the surface with a simple question. When you press send, where does your data actually go? When you press send, it feels immediate. You type a message. You tap a button. It appears somewhere else. Simple, clean, instant. But that feeling is an illusion. Not a deception, just a simplification. The Internet is designed to feel direct, as if one device speaks to another, as if a straight line connects them. There is no straight line. There is no single path. There is no continuous stream. Instead, there are fragments. Very small fragments. Organized, labeled, routed independently. When you press send, your message does not travel as one piece. It is broken apart into packets. A packet is a small unit of data, a container, a structured envelope. Inside that envelope is part of your message and information about where it should go. Think of it like mailing a book, but instead of sending the whole book, you tear it into numbered pages. Each page travels separately. Each page may take a different road. They may not arrive together. But if everything works, they are reassembled at the destination. And the book feels whole again. This is the first layer of the illusion. Continuity. Where there is fragmentation, you see a flowing conversation. The network sees numbered packets. You see a video playing smoothly. The network sees bursts of data. You see a file uploading. The network sees thousands of independent units. The illusion works because of timing. The packets move fast, very fast, often across continents, in fractions of a second. Speed hides complexity. But speed is not the same as simplicity. Now consider something else. When you press send, where do you imagine the message goes? Directly to the other person? Directly to the website? It rarely works that way. Your data usually travels through many devices first. Routers, switches, servers, sometimes dozens of them. Each device makes a small decision, not about meaning, not about content, only about direction. Where should this packet go next? That is the central question of the Internet. Not what the message says, but where it belongs. This leads to a second illusion. It's less than Hasson. Zero hash is greater than the illusion of intention. It feels like the network understands your request. It does not. It only follows rules. Structured rules, layered rules, predefined agreements. These agreements are called protocols. A protocol is simply a shared format, a shared expectation. If I send you data in this shape, you will know how to read it. If I label it in this way, you will know where it belongs. Protocols remove ambiguity. They replace understanding with structure. This is important. The Internet does not rely on intelligence. It relies on agreement. Agreement about how data is wrapped. Agreement about how it is addressed. Agreement about how it is acknowledged. Without those agreements, nothing connects. Now pause for a moment. When you open a messaging app, you see a conversation. You see names, profile pictures, timestamps. These are interface elements. They exist at the surface. Beneath them are layers. Layers that do not care about names. Layers that do not care about language. Only about bytes. A byte is just 8 bits, and a bit is just a 0 or a 1. At its core, your message becomes patterns of zeros and ones. Not sentences, not emotion, not tone. Patterns. Electrical signals, or pulses of light. The illusion of meaning sits on top of mechanical processes. This layering is intentional. Each layer solves a different problem. One layer defines how devices talk locally. Another defines how data moves globally. Another defines how applications format requests. They stack on top of each other, like transparent sheets. From your perspective, you only see the top sheet. That is by design. Complex systems survive by hiding complexity. If every message required you to understand routing tables, nothing would function at human scale. So the architecture separates concerns. Applications handle user interaction. Transport layers handle reliability. Network layers handle addressing. Physical layers handle signals. You press send, but many layers act. Now consider time. When a message feels instant, we assume it traveled instantly. It did not. It traveled at high speed. There is a difference. Signals in fiber optic cables move close to the speed of light, but not at the speed of thought. There is always delay, measured in milliseconds. Latency is small, but it exists. And every device in the path adds a small delay. Processing, forwarding, verifying. These delays accumulate. yet the system remains fast enough to feel continuous. That feeling is engineered. Now imagine something else. What if one packet is lost? It happens. Cables fail, routers overload, interference occurs. The system expects failure. It does not assume perfection. Some protocols require confirmation. If a packet does not arrive, it is sent again. Quietly, automatically. You rarely notice. Another illusion. Reliability feels inherent. But reliability is constructed through checksums, through acknowledgements, through sequence numbers. Small mechanisms, repeated billions of times per second. The Internet is not one machine. It is a coordination of many machines, owned by different companies, operated in different countries, connected by agreements. Yet when you press send, it feels unified. One action, one result. This is the power of abstraction. Abstraction removes details that are not immediately necessary. You do not see packet headers. You do not see routing hops. You do not see retransmissions. You see a delivered message. Delivered. Two small check marks. Behind those check marks is a distributed system coordinating across physical infrastructure. But that coordination begins somewhere simple. It begins on your device. Before packets cross oceans, before routers negotiate paths, before data centers respond, the message exists locally, in memory, as data structures. The illusion of sending starts with a local transformation. Text becomes bytes. Bytes become packets. Packets are handed to the network interface. And only then does the wider journey begin. So the illusion is not false. It is layered. At the human layer, you send a message. At the network layer, packets are routed. At the physical layer, signals move across copper and glass. All of this happens in less than a second. That is why it feels simple. But understanding begins when we slow it down, when we separate the layers, when we examine each step. We have started with the illusion. Next, we move closer. Closer to where the journey begins. In the devices we hold and the networks that surround them. Now we turn to devices and local networks. The journey begins on your device. Not in the cloud, not across the ocean. Here, in your phone, in your laptop, in your tablet. When you press send, the message first exists as data in memory. It is structured, encoded, organized into bytes. the operating system takes over. It prepares the data for transmission. This preparation follows rules. Layers again. Application layer, transport layer, network layer, link layer. Each layer adds information. Headers, labels, instructions. These instructions are not for humans. They are for machines. Now consider identity. On a network, every device needs an address. An identifier. Without identity, there is no direction. Inside your local network, your device has a private IP address. An IP address is a logical label. It tells the network where data should go. It does not describe location physically. It describes position within a network structure. But there is another identity, a physical one. The MAC address, Media Access Control Address. This is tied to your network interface card. It is more permanent. It operates at a lower layer. IP addresses change. MAC addresses usually do not. Two forms of identity: logical and physical. Both are used. Now pause and picture your room. There may be several devices connected. A phone, a laptop, a smart TV, maybe a game console, all connected to the same router. This small environment is a local network, also called a LAN, local area network. Within this LAN, devices communicate directly. They do not yet touch the wider internet. If you stream a video from your phone to your TV using Wi-Fi, the data may never leave your home. It stays local. The router coordinates this. A router is a decision maker. It examines destination addresses. It decides where packets should go next. Inside your home, it acts as a traffic director. If device A wants to speak to device B, the router forwards the packet internally. If the destination is outside the local network, the router prepares to send it outward. But before that outward journey begins, something important happens. Address resolution. Your device may know the destination IP address, but on a local network, data is delivered using MAC addresses. So the device asks a question. Who has this IP address? This is done using ARP, Address Resolution Protocol. It broadcasts a request within the LAN. The correct device responds with its MAC address. Now the packet can be delivered properly. This process is quiet, automatic. It happens in milliseconds. Again, the illusion holds. You do not see ARP requests. You do not see MAC tables. You see a message sent. Now let us look at the router more carefully. Your home router is several devices in one. It is a router. It is a switch. It is often a wireless access point. As a switch, it connects wired devices internally. It maintains a table of MAC addresses. It learns which device is on which port. As a wireless access point, it translates radio signals into network frames. Wi-Fi is not the Internet. Wi-Fi is simply a method of local wireless communication. It replaces cables with radio waves. The rules of networking remain. Packets are still structured. Addresses are still required. Now consider private IP addresses again. Inside your home, devices use ranges like 192.168x, x, or 10x, x, x. These are not globally unique. They are reused in millions of homes. This works because local networks are isolated from each other. Your 192.168.1.5 is not the same as your neighbor's 192.168.1.5. They exist in separate local contexts. This separation is essential. It conserves global address space. It also improves security. Devices inside your LAN are not directly exposed to the global Internet. The router acts as a boundary, a controlled gate. When your device wants to send data outward, it sends the packet to the router's local IP address. The router becomes the next hop. This idea of a next hop is central. Data rarely knows the full journey. It only knows the next step. Inside your home, the next step is the router. The router examines the destination IP. If it belongs to the local network, it forwards internally. If not, it prepares the packet for external travel. Before we leave the home network, notice the pattern. Identity, encapsulation, forwarding decisions. These ideas repeat at every scale. Small scale in your room. Large scale across continents. The structure is fractal in logic. Not mystical, just consistent. Now imagine multiple devices sending data at once. Streaming video, downloading updates, sending messages. The router queues packets. It manages traffic. It ensures fairness. Sometimes it drops packets if overloaded. Higher layers handle recovery. Again, coordination across layers. Nothing acts alone. Now we stand at the edge of the local network. Your packet has left your device. It has reached your router. It carries a private source IP. It carries a public destination IP. But private addresses cannot travel the global Internet. They must be translated. This translation happens at the boundary, at the router. And beyond that boundary lies a much larger network. To understand what happens next, we must expand our view beyond the home. Now we turn to the role of Internet service providers. Your packet has reached the edge of your home network. It now faces outward. Beyond your router is a larger system. This system is operated by your Internet service provider. An ISP is a company that connects your local network to the global Internet. It provides access. It maintains infrastructure. It assigns public identity. Without an ISP, your home network remains isolated. It can function internally, but not globally. Now recall that devices in your home use private IP addresses. These addresses are not valid on the public Internet. They must be translated. This process is called network address translation, often shortened to NAT. Your router performs NAT before traffic leaves your home. It replaces the private source IP with a public IP assigned by your ISP. This public IP represents your entire household. Multiple devices. One public identity. The router keeps track of which internal device started each connection. It uses port numbers to differentiate them. Ports act like internal room numbers. The public IP is the building address. Together, they allow return traffic to find the correct device. This mapping is temporary. It exists only while the session is active. NAT conserves global IPv4 addresses. It also adds a layer of separation. External systems cannot directly initiate connections to devices inside your home without configuration. The boundary is controlled. Now your packet carries a public source IP. It is ready to enter your ISP's network. What does that network look like? It is not a single cable. It is a hierarchy. At the lowest level is the last mile. The last mile connects your home to the ISP's local infrastructure. It may be fiber. It may be cable. It may be DSL over telephone lines. It may be mobile cellular. Different technologies. Same purpose. To move packets from your building to a nearby aggregation point. This aggregation point connects many customers. Your traffic joins others. From there, packets travel deeper into the ISP's core network. The core network consists of high-capacity routers and fiber links. These routers do not know you personally. They only know routing tables. A routing table lists destinations and the next hop required to reach them. Again, the idea of the next hop. Packets move step by step. Each router examines the destination IP. It compares it against known network prefixes. It forwards the packet toward the most appropriate next router. This happens extremely fast, measured in microseconds. Now consider scale. An ISP may serve thousands or millions, each customer generating traffic simultaneously. streaming video, making calls, loading websites. The ISP must manage congestion. It provisions bandwidth. It monitors usage patterns. It balances loads across links. Capacity planning is continuous because demand is unpredictable. Now step back. Your ISP connects you to its own network. But the Internet is not owned by one ISP. It is a network of networks. Each ISP operates its own autonomous system. An autonomous system is a large network under a single administrative control. It has its own routing policies, its own internal structure. Your ISP must connect to other autonomous systems. Otherwise, traffic would stop at its border. These connections happen through peering and transit agreements. Peering is often mutual. Two networks exchange traffic directly. Transit involves payment. One network pays another to carry traffic further. These relationships form a global mesh. Not perfectly uniform, but interconnected. Routing information between autonomous systems is shared using BGP, Border Gateway Protocol. BGP does not determine the shortest physical path. It determines the most policy-compliant path. Policies reflect business agreements. Economic realities shape technical routes. This is important. The Internet is technical and economic. Your packet's journey depends on both physics and contracts. Now return to your individual packet. It enters your ISP's edge router. It is forwarded into the core. If the destination is within the same ISP, it may stay internal. If not, it will approach an interconnection point. At that point, your ISP hands the packet to another network. Responsibility shifts. The packet continues. Notice the pattern again. Encapsulation, forwarding, handoff. Each boundary repeats the logic. Local network to ISP. ISP to larger backbone. Backbone to destination network. At no point does the packet understand the full route. Each router only knows the next step. Distributed knowledge. No single central controller. This decentralization increases resilience. If one path fails, routing tables update. Traffic shifts. The change may take seconds, sometimes less. Users rarely notice. End is less than #. 0 hash is greater than. Now consider performance. Your ISP influences latency. It influences bandwidth. It influences reliability. The physical distance to its infrastructure matters. The capacity of its backbone matters. Its peering relationships matter. Even though you only see a monthly bill, Behind that bill is a complex operational system. Engineers monitor traffic flows. They upgrade links. They mitigate outages. They manage routing announcements. All so that pressing send still feels simple. Now, one more detail before we move on. How does your device know where to send traffic in the first place? When you type a website name, you do not type an IP address. You type a domain. Human-readable. Memorable. But routers forward using IP addresses. So, somewhere before routing begins, a translation must occur. Names must become numbers. That translation does not happen inside core routers. It happens through a separate system, a global directory, distributed, hierarchical, quietly consulted before most connections begin. To understand how names become destinations, we now turn to DNS, the Internet's directory system. When you type a website name, you use words. Words are easy to remember. Words are for humans. But routers do not understand words. They understand IP addresses, numbers, structured numeric labels. So, before a packet can travel, a translation must occur. A name must become a number. This translation is handled by DNS, Domain Name System. DNS is often compared to a phone book. It maps names to numbers. But unlike a single book, DNS is distributed. There is no central master list stored in one place. Instead, DNS is hierarchical, layered, delegated. Let us slow this down. When you enter a domain in your browser, the browser asks the operating system for the corresponding IP address. The operating system checks its local cache first. If the answer is already known, the process ends quickly. Caching reduces repetition. It reduces delay. If the answer is not cached, the system contacts a DNS resolver. This resolver is usually provided by your ISP. It can also be a public resolver. The resolver's job is to find the answer on your behalf. It performs a recursive query. Recursive means it continues asking other servers until it finds the final answer. Now consider the structure of a domain name. Take an example like www.example.com. It has parts separated by dots. From right to left, the hierarchy becomes more specific. The rightmost part is the top-level domain. In this case, .com. Above that are root servers. Root servers know where to find top-level domain servers. They do not know every website's IP address. They only know where to direct the next question. Again, the idea of the next step. The resolver first asks a root server. The root server responds with the address of the appropriate top-level domain server. Then the resolver asks the top-level domain server. For .com, it asks the .com TLD server. The TLD server responds with the authoritative name server for example.com. Finally, the resolver asks the authoritative server. The authoritative server provides the IP address. Step by step. Delegation at each level. No single server holds all answers. This design increases scalability. It distributes responsibility. It prevents central overload. Now, consider time again. This entire sequence often completes in milliseconds because responses are cached. Resolvers store answers temporarily. Each DNS record includes a TTL, time to live. TTL defines how long the answer can be cached. When the TTL expires, the resolver must ask again. Caching balances freshness and efficiency. Frequent changes require lower TTL values. Stable domains can use higher TTL values. Now let us clarify something subtle. DNS does not move your data. It does not carry web pages. It does not transport videos. It only answers one question. What is the IP address for this name? Once the IP address is known, normal routing begins. DNS is a prerequisite, not the delivery mechanism. Now consider different types of DNS records. An A record maps a domain to an IPv4 address. An AAA record maps to an IPv6 address. A CNAME record maps one domain name to another. MX records define mail servers. TXT records store arbitrary text data. DNS is flexible. It stores structured information, not just simple name-to-number pairs. Now, think about reliability. What if a DNS server fails? The system anticipates this. There are multiple root servers distributed globally. Each is replicated across many physical machines. Top-level domain servers are also redundant. Authoritative servers are often deployed in clusters. Redundancy is built in. Because without DNS, users cannot find destinations. Even if the destination server is functioning. Now consider privacy and security. Traditional DNS queries are not encrypted. They can be observed in transit. To address this, newer protocols exist. DNS over HTTPS. DNS over TLS. These encrypt DNS queries between your device and the resolver. The goal is confidentiality. Another security layer is DNSSEC, Domain Name System Security Extensions. DNS-SEC adds cryptographic signatures to DNS data. It allows resolvers to verify authenticity. It reduces the risk of spoofed responses. Security adds complexity. But it follows the same principle. Layered mechanisms. Independent roles. Now step back once more. When you type a domain, a quiet conversation begins between your device and resolvers, between resolvers and authoritative servers. A chain of questions, a chain of referrals, until a number is returned. That number becomes the destination IP. Only then can packets be routed across networks. DNS feels invisible because it completes before the page loads. But without it, names would have no meaning to machines, and humans would have to remember numbers. The directory system stands between language and routing, between words and packets. Now, the name has become an IP address. The resolver's work is done. The browser now prepares to open a connection. This connection will rely on structured data units. Encapsulated, sequenced, verified. To understand how these units are formed and controlled, we must look closer at packets and the rules that govern them. Now the destination IP address is known. The browser is ready to communicate. But communication on the Internet does not begin as a continuous stream. It begins with packets. A packet is a structured unit of data. It is not just raw content. It contains control information. It contains addressing information. And it contains a fragment of payload. The payload is the actual data being sent. The rest is metadata. Data about the data. This structure allows independent handling. Routers read headers. They do not read the payload. They forward based on addresses. Now, let us examine layers again. When an application sends data, it passes through multiple protocol layers. Each layer adds its own header. This process is called encapsulation. Imagine placing a letter inside an envelope, then placing that envelope inside a larger envelope. Each layer wraps the previous one. At the transport layer, the most common protocol is TCP. Transmission Control Protocol. TCP is designed for reliability. It ensures ordered delivery. It ensures completeness. Before data flows, TCP establishes a connection. This begins with a handshake. A three-step exchange. SYN. SYNAC. AC. Synchronization. Agreement to communicate. Only after this handshake does data transfer begin. TCP divides the data into segments. Each segment is numbered. Sequence numbers allow reordering at the destination. If a segment is lost, the receiver notices a gap. It requests retransmission. Acknowledgements confirm successful receipt. This is reliability through confirmation. But TCP is not the only transport protocol. There is also UDP, User Datagram Protocol. UDP is simpler. It does not establish a formal connection. It does not guarantee delivery. It does not guarantee order. It sends packets and moves on. This may sound less reliable, but it is faster. And sometimes speed matters more than certainty. Streaming video often uses UDP. Real-time gaming often uses UDP. Small losses are tolerated. Delays are not. Different needs require different protocols. Now move one layer down. Below the transport layer is the Internet Protocol. IP handles addressing and routing. It defines source and destination IP addresses. It does not ensure delivery. It does not ensure order. It provides best effort delivery. Best effort means the network tries, but does not promise. Reliability is left to higher layers like TCP. This separation keeps responsibilities clear. Now consider fragmentation. Networks have maximum transmission unit sizes, often around 1,500 bytes for Ethernet. If a packet exceeds this size, it must be fragmented, broken into smaller pieces. Each fragment travels independently. They are reassembled at the destination. Fragmentation adds overhead. It can reduce efficiency, so systems often try to avoid it. Now return to encapsulation. At the transport layer, we have a TCP segment. This segment becomes the payload of an IP packet. Then that IP packet becomes the payload of a data link frame. On Ethernet, this frame includes MAC addresses. At the physical layer, frames become signals. Electrical pulses, or light pulses in fiber. Each layer interprets only what it needs. Routers examine IP headers. Switches examine MAC addresses. Applications interpret payload data. Layered responsibility. Now consider ports. An IP address identifies a device. A port identifies a service on that device. Web servers often use port 80 for HTTP, or port 443 for HTTPS. Email servers use other ports. Ports allow multiple services to operate on one machine. When your browser connects to a server, it specifies a destination port. The server listens on that port. This is how traffic reaches the correct application process. Now think about flow control. TCP adjusts transmission speed based on network conditions. If acknowledgements arrive quickly, the sender increases the rate. If packets are lost, it slows down. This prevents overwhelming the network. It prevents congestion collapse. Congestion control is dynamic. It responds to feedback. Now pause and observe the pattern. Addressing, sequencing, acknowledgement, encapsulation. Every packet carries structure. Every protocol defines behavior. Protocols are agreements. They define formats. They define timing. They define error handling. Without protocols, packets would be meaningless. They would be random bits. With protocols, independent machines cooperate. Now consider encryption briefly. When using HTTPS, data is encrypted before being placed inside TCP segments. Encryption happens at a higher layer. Routers still forward packets normally. They cannot read the encrypted payload. They only read addressing information. This separation allows privacy without changing routing infrastructure. Now imagine thousands of packets forming a web page. HTML files, CSS files, JavaScript, images, each delivered in packets, each verified, each reassembled. The browser waits until enough data arrives. Then it renders the page. What feels continuous is discrete underneath. Structured units moving independently. Packets are the currency of the Internet. Protocols are the rules of exchange. Together they form a predictable system. A system that scales across continents. But packets do not float randomly. They follow routes. They traverse networks controlled by different organizations. To understand how these paths are chosen across vast distances, we now turn to routing across the world. Packets now exist. They carry source and destination addresses. They are ready to travel. But how do they know where to go? They rely on routing. Routing is decision-making at scale. It determines the next hop, not the entire path at once. Just the next step. This is an important detail. Routers do not calculate the full journey. They forward step by step. Each router consults its routing table. A routing table is a structured list. It maps destination IP ranges to next hop addresses. It also includes metrics. Metrics express preference. Lower cost routes are preferred. Higher cost routes are secondary. Now pause. Think of routing as distributed knowledge. No single router knows the entire Internet in detail. but each router knows enough to move the packet closer to its destination. This incremental progress is powerful. Now consider scale. The global internet contains millions of networks. These networks are grouped into autonomous systems. An autonomous system is a collection of IP prefixes under one administrative control. Internet service providers operate autonomous systems. Large companies operate autonomous systems. Universities may operate their own. Each autonomous system has a unique number, an ASN. Within an autonomous system, routing is handled by interior gateway protocols. Common examples include OSPF and IS-IS. These protocols share information about internal topology. They calculate shortest paths. They update when links change. They converge after disruption. Convergence means agreement. All routers reach a consistent view. This process is continuous. Now move beyond a single organization. Between autonomous systems, routing uses a different protocol. The Border Gateway Protocol, BGP. BGP is the protocol of the global internet. It exchanges reachability information. It does not calculate shortest path in the traditional sense. It selects paths based on policy. Policy reflects business relationships, transit agreements, peering agreements, customer relationships. This is important. The internet is technical, but also economic. Packets often follow financially sensible routes, not always the geographically shortest. Now consider how BGP works at a high level. Each autonomous system advertises the IP prefixes it can reach. It includes the path of AS numbers to reach that prefix. This is called the AS path. When another system receives this advertisement, it evaluates it. It applies policy rules. It selects one best path. It then advertises that choice onward. In this way, reachability information propagates across continents. Slowly, incrementally. Now, think about redundancy. The internet is designed with multiple paths. If one link fails, another can carry traffic. Routing protocols detect failure. They withdraw routes. They announce alternatives. This takes time, but usually seconds, sometimes milliseconds within local networks. Resilience is achieved through diversity, not through central control. Now consider latency. Each hop introduces delay. Processing delay at the router. Queuing delay if traffic is heavy. Transmission delay based on link speed. Propagation delay based on physical distance. Routing decisions influence total latency, but they balance many factors: policy, stability, capacity. Now reflect on the journey of a single packet. It may leave your home router, enter your ISP's regional network, travel to a major exchange point, cross into another provider's backbone, traverse long-haul fiber, reach a data center in another country. All decided hop by hop, without a central map. Now consider internet exchange points. These are physical locations. Multiple networks connect there. They exchange traffic directly. This reduces cost. It reduces latency. It keeps local traffic local. Large cities often host major exchange points. They are hubs in the global topology, but still decentralized. Now think about routing stability. Frequent changes can cause instability, so protocols dampen rapid fluctuations. They prefer stable paths, even if slightly longer. Stability supports predictability. Predictability supports scale. Now consider security briefly. BGP was designed in a more trusting era. It assumes truthful announcements. But misconfigurations occur. Sometimes malicious announcements occur. This can redirect traffic incorrectly. To address this, additional security mechanisms are being deployed, such as route validation systems. These improvements are gradual, incremental, like much of the Internet. Now pause again. Routing is continuous negotiation between machines, between organizations, between policies. Packets move because many systems cooperate, each enforcing its own rules, yet still participating in a shared network. No single authority directs global routing. It emerges from interaction. Now return to the packet itself. At each router, the header is examined. The destination prefix is matched. The next hop is selected. The packet is forwarded. This repeats again and again until the destination network is reached. Then local routing takes over. Finally, the packet arrives at the target server. Routing appears abstract, but it depends on very physical systems. Routers in racks, cables under streets, fiber under oceans. To understand routing fully, we must now look beneath the logical layer and examine the cables, data centers, and signals that carry packets across the planet in Section 7, Physical Infrastructure. So far, we have spoken about logic, about addresses, protocols, routing decisions. Now we move lower. Beneath software, beneath abstraction, into the physical layer. The Internet is not weightless. It is made of hardware, cables, switches, routers, data centers. Signals move through matter. Let us begin with the simplest connection. Your device connects to a local network, often through Wi-Fi, or through an Ethernet cable. Wi-Fi uses radio waves. Ethernet uses copper wiring. In both cases, bits become signals. Electrical changes in voltage, or electromagnetic waves through air. These signals travel short distances, from device to router, from router to modem, then outward to your Internet service provider. Now pause. At this early stage, distance is small. Meters, perhaps tens of meters. But soon, distance expands. Your ISP connects to regional infrastructure. This is often fiber optic cable. Fiber is different from copper. It carries light, not electricity. Inside a fiber strand is glass. Very pure glass. Light pulses travel through this glass, reflecting internally, maintaining signal integrity across long distances. Light travels extremely fast. Not faster than in a vacuum, but close. This allows high bandwidth, large volumes of data. Now consider capacity. A single fiber strand can carry enormous throughput, using wavelength division multiplexing. Different colors of light carry separate channels. Each channel carries independent data streams, all within one physical cable. Capacity scales by adding wavelengths, or by laying more fibers. Infrastructure grows incrementally. Now, extend the distance again. Cities are connected by long-haul fiber. Countries are connected by national backbones. Continents are connected by submarine cables. These cables lie on ocean floors, thousands of kilometers long. They are engineered carefully, protected with layers of shielding, monitored constantly. Submarine cables carry the majority of international Internet traffic. Satellites exist, but fiber carries more data with lower latency. Signals weaken over long distances, so repeaters are placed along submarine cables. They amplify the light signal. They require power. Power is supplied through the cable itself. Physical engineering supports digital communication. Now consider landing stations. Submarine cables do not float freely. They land at controlled facilities on coastlines. These landing stations connect ocean fiber to terrestrial networks. From there, traffic moves inland. toward exchange points and data centers. Now shift attention to data centers. Data centers house servers, racks of machines, arranged in rows, connected by high-speed switches. They provide storage, computation, and network connectivity. Large services replicate data across multiple data centers, often across regions. This reduces latency. It increases resilience. If one facility fails, another continues. Now think about environmental requirements. Servers generate heat. Heat must be removed. Cooling systems operate continuously. Power must be stable. Backup generators are installed. Battery systems bridge short outages. Redundancy is built into design. Physical resilience mirrors logical resilience. Now consider network hardware itself. Routers are specialized devices. They process packets at high speed, often using dedicated hardware chips. Switches connect devices within local networks. They forward frames based on MAC addresses. Core routers handle enormous traffic volumes. Edge routers connect customers. Each device occupies physical space. Each requires power and cooling. Now pause and observe the scale. Millions of kilometers of fiber. Thousands of data centers. Countless routers and switches. All coordinated through protocols we discussed earlier. The logical and physical layers interlock. One cannot exist without the other. Now consider the last mile. This is the connection from ISP to end user. It may use fiber to the home, or cable broadband, or DSL over telephone lines, or fixed wireless links. The last mile often determines user experience. Bandwidth limits may appear here. Latency may increase here. Infrastructure investment varies by region. Physical geography matters. Urban areas differ from rural areas. Mountains differ from plains. Infrastructure follows terrain. Now think about signal conversion. At each boundary, signals may change form. Electrical to optical. Optical back to electrical. Digital logic remains consistent, but the medium shifts. Hardware performs these translations quietly, continuously. Now consider maintenance. Cables can be cut accidentally. Construction projects sometimes damage fiber. Ships' anchors can affect submarine cables. Monitoring systems detect disruptions. Traffic reroutes automatically when possible. Repair teams are dispatched when necessary. Physical reliability requires ongoing effort. Now, pause once more. When you load a web page, you activate this entire chain from your device's antenna to neighborhood wiring to regional fiber, across oceans, into data centers, and back again, all within fractions of a second. The internet feels intangible, but it is deeply physical. Glass strands, metal racks, concrete buildings, power grids, cooling systems. The abstraction rests on infrastructure, and infrastructure shapes performance. Now that we understand the cables and facilities that carry packets across the world, we can move back up the stack and examine how browsers and servers interact in the web layer. We now move upward again. From cables, from routers, from packets, to the layer most people recognize: the web. The web is not the internet itself. It is an application that runs on top of it. It uses the infrastructure we have described, but it adds its own structure, its own rules, its own language. At the center of the web is a simple pattern: request, response. A client makes a request. A server sends a response. The client is usually a browser. The server is a machine in a data center. This pattern is repeated constantly, quietly. When you type a web address, the browser prepares an HTTP request. HTTP stands for Hypertext Transfer Protocol. It defines how requests are formatted. It defines how responses are structured. An HTTP request contains a method, often GET, sometimes POST. The method describes intent. GET asks for a resource. POST submits data. The request also contains headers. Headers carry metadata, information about the client, accepted formats, cookies, and other details. Then the request travels through TCP, through IP, across physical infrastructure, until it reaches the server. Now pause. At the server, software listens for incoming requests. This software is called a web server. It might be a dedicated program or part of a larger application framework. When the request arrives, the server interprets it. If the request is for a static file, the server retrieves it from storage. If the request requires computation, application code runs. This code may query a database. It may assemble content dynamically. It may apply authentication checks. Then the server prepares a response. An HTTP response contains a status code. 200 means success. 400 codes indicate client errors. 500 codes indicate server errors. The response also includes headers and a body. The body often contains HTML. HTML stands for Hypertext Markup Language. It describes structure, headings, paragraphs, links. The browser receives the response. Then it begins rendering. Rendering is interpretation. The browser parses HTML. It builds a document object model, often called the DOM. The DOM represents the page as a tree structure. Nodes connected hierarchically. Now consider styling. HTML defines structure. CSS defines presentation. CSS stands for Cascading Style Sheets. It specifies colors, fonts, spacing. The browser downloads CSS files separately. These are additional HTTP requests. Each request follows the same pattern. Request, response. Now consider behavior. JavaScript adds interactivity. It runs inside the browser. It can modify the DOM. It can respond to user input. It can make additional network requests, often using APIs. APIs expose structured endpoints. Returning JSON data. JSON is a lightweight data format. It represents objects and arrays. This allows dynamic updates without reloading the entire page. Now pause again. What appears as one page load is often dozens of requests. HTML, CSS, scripts, images, fonts, each retrieved separately, each traveling as packets. The browser manages these concurrently. It opens multiple connections or reuses existing ones. Now consider HTTPS. Most web traffic today is encrypted. HTTPS is HTTP over TLS. TLS stands for Transport Layer Security. Before regular HTTP data flows, a cryptographic handshake occurs. The server presents a digital certificate. The browser verifies it. Keys are exchanged. A secure session is established. After that, HTTP messages are encrypted. Intermediary routers still forward packets, but they cannot read the contents. Confidentiality is layered above transport. Now consider caching. Not every request travels to the origin server. Browsers cache resources locally. Servers send cache control headers. These headers specify expiration rules. If content is fresh, the browser reuses it. This reduces latency. It reduces bandwidth usage. Content delivery networks also assist. They replicate content across many locations. Users connect to nearby servers. Physical distance decreases. Response time improves. Now reflect on abstraction. The web hides complexity. You see text and images. You click links. You submit forms. Underneath, structured exchanges occur. Formatted messages. Defined protocols. Layered encryption. Concurrent resource loading. All resting on the Internet's architecture. Now consider state. HTTP is stateless by design. Each request is independent. The server does not inherently remember previous requests. State is simulated using cookies or session tokens. These identifiers allow continuity. Login sessions, shopping carts, user preferences, stateless protocol, stateful experience. Now think about performance again. Modern versions of HTTP improve efficiency. They allow multiplexing, multiple requests over a single connection. Header compression reduces overhead. Persistent connections reduce setup cost. The protocol evolves, but the core pattern remains. Request, response. Now pause for a final reflection in this section. When you open a website, you engage every layer we have explored. DNS resolves names. TCP establishes connections. IP routes packets. Fiber carries light. Servers generate responses. Browsers render structure and style. All within seconds. Often within fractions of a second. The web is a coordinated system. Layered, structured, interdependent. And now that we have traced data from name resolution through physical cables to rendered pages, we can step back and examine how the system maintains reliability, manages delay, and continues evolving in Section 9. Resilience, latency, and the future. We now step back. We have followed data from names to packets to cables to rendered pages. Now we consider stability. We consider delay. And we consider what comes next. Resilience is the Internet's quiet strength. It is not a single feature. It is a pattern of design choices. Redundancy is everywhere. Multiple paths between networks. Multiple servers hosting the same content. Multiple data centers in different regions. If one component fails, traffic shifts. Routing protocols withdraw broken paths. Alternative routes are selected, often automatically, often within seconds. This is distributed resilience. No central switch restores the system. Local decisions accumulate into global recovery. Resilience also exists at higher layers. TCP retransmits lost packets. Applications retry failed requests. Browsers cache resources. Content delivery networks replicate data widely. Each layer assumes failure is possible and prepares for it. Failure is not exceptional. It is expected. This expectation shapes the architecture. Now consider latency. Latency is delay. The time between request and response. It is influenced by distance. Signals cannot travel instantly. Even light in fiber has limits. Propagation delay increases with geography. But distance is not the only factor. Each router introduces processing time. Each queue introduces waiting time. Congestion increases delay. Encryption handshakes add initial overhead. DNS lookups add time at the beginning. Many small delays accumulate. This accumulation shapes experience. Engineers work constantly to reduce latency. Servers are placed closer to users. Edge computing moves computation outward. Protocols are refined. Connections are reused. Data is compressed. Yet some delay will always remain. Physics sets boundaries. Architecture works within them. Now think about scalability. The Internet has grown for decades. New devices join continuously. New services emerge. Traffic volumes expand. Scalability depends on decentralization. Networks manage themselves locally. Protocols summarize information. Routing tables aggregate prefixes. Hierarchies limit complexity. This prevents any single device from needing full global knowledge. Scale is achieved through structure. Security remains an evolving challenge. Encryption is now standard for the web. Authentication mechanisms are improving. Routing security is being strengthened. Yet the Internet remains open by design. Openness enables innovation. It also requires vigilance. The balance is ongoing. Now consider reliability at the human level. Operators monitor networks continuously. Engineers respond to outages. Standards bodies refine protocols. Collaboration occurs across organizations. The Internet is technical infrastructure, but also cooperative infrastructure. Shared agreements sustain it. Looking forward, change will continue. New transport protocols are being adopted. More encryption by default. Greater automation in routing management. expanded fiber networks, low Earth orbit satellite constellations extending coverage, increased edge computing to reduce latency. The architecture evolves incrementally, rarely through sudden replacement, more often through layering and refinement. Despite growth, the core principles remain stable. Packets, layering, decentralized routing, redundancy. These foundations have endured. They allow adaptation without collapse. They support billions of users. Quietly, continuously. When you send a message or open a page, you participate in this system. A system designed for resilience, shaped by latency constraints, guided by open standards, and still evolving. The Internet is not finished. It is maintained, adjusted, extended. Its future will likely remain layered and distributed, built on the same quiet principles we have explored. We have traced the path of data, from names to numbers, to packets, to cables beneath oceans. We have seen how layers cooperate, how protocols define behavior, how routing decisions move information step by step. The Internet is not a single machine. It is a coordinated structure, distributed, redundant, continuously maintained. Most of the time, it feels effortless. Pages load, messages arrive, videos stream. Beneath that ease is careful design. And now you have seen the architecture beneath the surface. Not as abstraction, but as layered systems working together. The next time you open a browser, you may notice the quiet complexity supporting that simple action. The Internet continues to move data. Calmly, reliably, one packet at a time.